Okay, it's a video about B1, and that's curve sketching. And we're just going to put it all together. So everything we know about curve sketching is in this video. Okay, so first I wrote a little algorithm for curve sketching. There's one in your textbook too, and they're not exactly identical, but these are kind of like the 6 steps I use, and not necessarily in this order, and not necessarily for each type of function. You're already kind of familiar with shapes of graphs from taking advanced functions and functions. So, like, you know, when you see an equation, like f of x equals x squared plus 1, you already have a picture of what that looks like in your mind. You already know that's going to be a parabola. You might already know that that shifts it up 1. So you kind of know, like, the general shape of the graph. If you see a graph that's like this, maybe you know right away, oh, that's a rational function. I don't know exactly what it looks like, but I feel like it's going to be like some kind of graph like that with some asymptotes. I don't know exactly, but something like that. If you look at, if someone gives you like a square root graph, then you maybe know, oh, I know they look like that. So just from looking at the function itself, you probably already have some ideas of what the graph's going to look like. We just want to get more accurate. Okay, so just to go over this list, it's in the class notes too, so you can access it. But first I'm going to check out the domain of the graph just to see if there's any discontinuities in the function. So just see if it's available or if it goes through every value of x. Then you want to check for asymptotes on your graph. So if there's any vertical asymptotes or horizontal asymptotes, like if you have a rational function, you know you have a denominator and you know you don't want a denominator to equal 0 ever, so it's going to produce an asymptote. I did a whole video, I think, on stuff from advanced functions, which asymptotes was in there. Okay, and then intercepts, like it's a good idea to find your x and y intercepts if it's easy enough to do it, because then you'll have a more accurate graph. And critical numbers, that's what we learned this year. That's when we set our derivative equal to 0, because if you think about it, if you had a graph out like this, at these points is when the derivative is 0, because that's when they'll have a slope of 0. So at those points, the critical numbers, that finds the maxes and mins, and they can be local max and mins, like these two. Like this would be called a local maximum. It's not the absolute max of the graph because the graph keeps going, but it is the local max, and this guy would be like a local min. So that's what critical numbers are. They can find those values. So you want to find them and you want to classify them. Are they maximums? Are they minimums? And we have a couple ways of doing this. We can use the derivative and figure out if it goes from like an increasing, like a positive function, to decreasing, to negative. So we can check out the value of our slopes. And as long as it switches from positive to negative or negative to positive, that can tell us about local max and mins. And we can also use the second derivative to tell us. And then we have points of inflection. So that's when our second derivative is equal to 0. And that's where graphs change from having local maxes to local minimums. You'll have a point of inflection in there. Or from minimums to maximums. Same thing. And intervals of increase and decrease, that's just if your graph has got a positive slope or a negative slope. So all of these things, we don't necessarily use all of them, but they help us sketch an accurate graph. Okay, so let's sketch this really tricky polynomial. So first of all, I know it's polynomial. So it's going to look something like that, or I don't know, who knows. Well, although I do know it's a 4th degree polynomial, so for my advanced functions knowledge, I know that 4th degree functions are going to start and end in like the top or the bottom. So like it's gonna go like this, or maybe it's gonna go like this. And I know now, because the leading coefficient is a positive value, it's actually gonna be this one. So it's gonna start and end in quadrant 1 and 2. Okay, cool. So I kind of just know the general shape. I know all polynomials have a domain that's defined for all values of x. So I don't have to worry about that, but I'll just write it down so we know. So my domain is defined for all values of x, so I might want to just say that. And how do I know that? Because I know that all polynomials have that domain. I know rational functions are defined for all values of x except at the asymptotes. There's lots of things that you just should know from dealing with these graphs. There's no shortcut way to get them. Okay, next I want to find, what's step 2? Asymptotes. So I know there are no asymptotes here. There's nothing x can't be. And there's nothing any value is going to start approaching. And then third, I got to find my intercepts. Okay, so one of them I can see like super easily. That guy right there. I know that's my y-intercept, because if I set x equal to 0, I would get y equals -18. So I know I'm going to have a point at 0, -18. And to get the x-intercept, I'll definitely need to factor this. So let's just go ahead and do that. We could probably use a refresher. So using long division or synthetic, whatever your choice is, you would look for factors by examining this value here and picking multiples of that. So for example, I could try 1. And I would just sub 1 into the equation. So this is the factor theorem or remainder theorem. 1 to the power of 4 minus 5 times 1 cubed plus 1 squared plus 21 times 1 minus 18. And if I do that math, it actually equals 0. So I know that x equals 1 is going to be a root. So therefore, x minus 1 is going to be what I can factor out. So I'm going to do long division just to recap that, and I'll recap synthetic too. This could potentially be the longest video in the world. Okay, here we go. So how many times does x go into x to the power of 4? It goes in x cubed times. And then we just multiply x cubed by these two values here. So x cubed times x is x to the power of 4. X cubed times -1 is -x cubed. And then I subtract those. So x to the 4 minus x to the 4 is 0. -5x cubed minus -x cubed is -4x cubed. And then I bring down my next term, which is x squared. You do need to make sure that all your terms go in order. So like 4, 3, 2, 1, 0. If they don't, you have to add in a 0 term. Okay, so then how many times does x go into -4x cubed? It goes in -4x squared times. Okay, now we multiply -4x squared by x, and we get -4x cubed, and then we multiply it by -1, and you get positive 4x squared. Okay, then we subtract again. Then we get -3x squared, and we bring down the 21x. And we do the same thing. How many times does x go into -3x squared? -3x times. And we multiply it. -3x times x is -3x squared. And positive 3x. And then we subtract. Every time you subtract, your first terms in each expression should go away, which they do. So then 21 minus 3 is 18x. And then we bring down our final number, -18. And that goes in positive 18 times, leaving us with 0 remainder. Perfect. So now we take this and this, and we've got it partially factored. So I'm just going to rewrite that. So now we've got f of x is equal to x minus 1, x cubed minus 4x squared minus 3x plus 18. Okay, cool. So we're partway done. We factored out an x minus 1, but we still need to factor the x cubed expression. So let's try synthetic. So we're going to factor this guy. So remember synthetic, you put that, and then you write the coefficients. So the 1, the -4, -3, 18. And then you write your factor out here. So we got to find a factor by looking at 18. So let's say we tried, because I tried these ahead of time, so I already know. 3. If I sub in a 3, 3 cubed minus 4 times 3 squared, etc., that's going to equal 0. Okay, so 3 is our factor. I'm going to write a 3 there. Okay, so how we do synthetic is we bring the 1 down, boom. Then we multiply. So 3 times 1 equals 3. We write it there. And then we add between the rows. So -4 plus 3 would equal -1. Then we multiply. 3 times -1, -3. Then we add -3 plus -3, -6. Now we multiply. 3 times -6 is -18. And we add for a 0 remainder. And then now you know that 3 was actually like your root. So technically, so if we're writing this expression, so we've got the x minus 1 already. That just stays there. Then this 3 is a factor, so, or is a root. So in a bracket, I would write it as x minus 3, since 3 is the actual root. And then to get my final bracket, I would use these as my coefficients. And I know it's going to be 1 degree less than what I started with. So I started with the cubic function. So now it's going to be quadratic. It's going to be 1x squared minus x minus 6. Okay, and then I got to factor that one more step. I'm almost done. Now I've got a trinomial. So what multiplies to -6 and adds to -1? How about -3 times +2? And there you go. Fully factored. And you could actually write it, since we've got two x minus 3 brackets, we could write it as x plus 2 times x minus 1 times x minus 3 squared. Okay, so that's our fully factored function. So now we know we have x-intercepts at -2, 1, and 3. So we have 3 x-intercepts. Perfect. Okay, I feel like I should be, maybe in black, I will just box in all the special points. Everything I want to use in my graph. Okay, so I got that stuff. All right, moving on. What's after intercepts? Critical numbers. So step 4, that's what we're on. Critical numbers. That's your maxes and your mins. Okay, so to find it, we need to take the derivative. So f prime of x is equal to, I'm going to take the derivative of not the factored one. That would be a nightmare. Okay, so let me just copy this equation. Just going to pop it there for reference. Okay, so if we're taking the derivative, we're using power rule. That's pretty much it. So we got 4x cubed minus 15x squared plus 2x plus 21. Okay, so there's our derivative. And to find our max and mins, we have to set the derivative equal to 0. Looks like we need to do more factoring. Because now we're trying to solve for x, but the only way to do that is to factor it. Oh, so you get to practice factoring again. If you want to practice, just pause the video and then you can try it yourself. Okay, so first step, we got to find a factor. multiples of 21. Let's try x equals 3. Oh, it's going to work. And let's synthetic because it's way faster. So I'm going to write my coefficients for negative 15 to 21. 3 is my root. I'm going to bring the 4 down. Then I'm going to multiply to get 12. I'm going to add the columns. So negative 15 plus 12, I need negative 3. And then I'm going to multiply, get 9. I'm going to add negative 7. Multiply, boom, 0 remainder. Okay, so if you're still with me, this 3 becomes a bracket that's x minus 3. And then these guys are coefficients. So 4x squared minus 3x minus 7. Cool, and then you'd have to complex trinomial factor that guy. So what multiplies to negative 28 and adds to negative 3? Multiplies to negative 28 and adds to negative 3. How about 7 and 4? Okay, so really quickly off to the side, I'm just going to do that. Okay, so I got negative 7x. Oh my gosh, I'm not going to do it that way. I'm going to do positive 4x first. Negative 7x minus 7. Then I'm going to common factor out of 4x, leaving x plus 1. I factor out of negative 7, leaving x plus 1. So that factors into x plus 1, 4x minus 7. That's just a complex trinomial. Okie doke. So, final step. Done. Factored. Now I gotta find what, I forget what I was even finding. Critical numbers. Okay, we got them. Our critical numbers are 3, negative 1, and 7 over 4, which is also 1.75. Okay, cool. We got 3 critical numbers. So some of them are maxes, some of them are mins. We don't know. Why don't we find out? How could we do that? Let's classify these guys. Okay, first I'm going to put a box around them. Oh, actually, I'm going to hold off because I should get the y values before I do that. All right, so I'm going to get the second derivative. F double prime of x is equal to, okay, let's see here. Second derivative is 12x squared minus 30x plus 2. Awesome. So if I sub in a critical point, so let's start with our smallest guy, negative 1. So let's sub negative 1 into our second derivative. So if I actually subs that in, 12 times negative 1 squared, etc., I get 44. So since the second derivative is greater than 0, I have a local minimum at x equals negative 1. So since the second derivative is greater than 0, I have a local minimum. And to sub that guy back into the, like if I sub negative 1 back into my original equation, this guy, I can actually find the y value. So like negative 1 to the power 4 minus 5 times negative 1 cubed. I'm just finding the point that that critical point occurs at. So there's actually a local min at negative 1 and negative 32. So I just already did that math ahead of time. So I'm just going to circle that because that's a super important point that we'll have to plot. Now we need to do the second derivative for 3 and 1.75. So if we sub 3 into that second derivative equation, it's going to equal 20. So since the second derivative is greater than 0, we've got ourselves another local minimum at x equals 3. And if I sub 3 into, boom, my original guy, then I get a y value of 0. 0. Do I have an x-intercept at 3? I sure do. Okay, that makes sense. Okay, cool. So one of our x-intercepts is actually a local minimum. Okay, and then finally, let's sub in 1.75, or 7/4. If I sub that in, I actually get negative 13.75. So since my second derivative is now less than 0, I'm going to have a local max. And that's going to occur at 1.75 and 4.4. Okay. I have lots of information. Got a bunch of maxes and mins. Okay, next step. We got our critical numbers. Done. Now, let's, wait, what was that? Number 5, step 5. Let's find our points of inflection, if we have any, which I'm sure we do. Okay, so we find points of inflection by setting the second derivative equal to 0. So I know the second derivative is 12x squared minus 30x plus 2. Sorry about all the pen noise. Okay, so let's set that equal to 0. And, oh my gosh, do we get to factor again? You know what? Let's just divide everything in this by 2 for starters, because why not? It's nicer when the numbers are smaller. And is there anything that multiplies to 6 and adds to negative 15? I think no. So that's what that means. Your best friend, the quadratic formula, to the rescue. Okay, so quadratic formula is going to help you find your points of inflection. Now, here's where we would get hung up. If this was a cubic or something and we couldn't factor it, I'm not going to give you ones like that because we don't have a solution option at that point. Okay, so if we did quadratic formula, so negative b plus or minus the square root of b squared minus 4ac, and the whole thing is divided by 2a. If you actually calculate that, you're going to get two values. You're going to get 0.07 and 2.43. So we want to check to see if those are in fact points of inflection, because they might not be. So we just want to make sure. Okay, so to check if they are points of inflection, we want to check that the sign changes from concave up. We want to check that the graph changes from concave up to concave down. So it goes from like a max to a min, or a min to a max. So if we wanted to officially check that, let's say we check this guy. We pick values on either side of that point. So let's say we subbed in to the second derivative 0, because that's on one side. So if we sub 0 in, like to the second derivative, so 12 times 0 squared minus 30 times 0 plus 2, we get 2. So if the second derivative is positive, we know that the graph will be concave up. Because remember, if the second derivative is greater than 0, we get a local minimum. So concave up is like that. So that's like a minimum. Okay, and then if we pick a value on the other side of 0.007, like 1, and we sub that into like 12 times 1 squared minus 30 times 1 plus 2, sub that in, then we get negative 16, which indicates that your graph is concave down at that point, like so. So since our graph goes from concave up to concave down, this is a point of inflection. Perfect. And then you would do the same thing for 2.43. You would check values on either side. So you would check the second derivative at 2, and then it doesn't matter what values you pick as long as one's to the left and one's to the right. One's bigger, one's smaller, and you can see what's going on. So if you actually subbed these values into the second derivative, you get negative 10 for this one, and you get 20. So you know this one's going to be concave down, because it's a maximum there, and this one's going to be concave up. So therefore, that other guy is a point of inflection also. Oh my gosh, we're almost done. We have basically everything we need to know. But the one other thing that you might find handy, step 6, I called it intervals of increase and decrease, and also concavity. I'll just do this in purple. What are we on? Step 6. So we'll call it intervals of increase and decrease and concavity. So I don't know the size of table you want to make. Like, you can get really specific, and this is a quartic function, so it's really big. There's a lot of important points here. But basically, you want to make a table that goes through all the intervals of your graph. So if you think about it, your super special points are, you have 2 inflection points, and you have 3 maxes and mins. So those are all your really important points. So since we have so many, I'm just going to use my critical values as my kind of like important spots, but you can also use your points of inflection. It's kind of up to you. So what I'm saying is, if you're going to make yourself a little table here, and we're almost done. Sorry, I'm going to wrap this up real soon. Thanks for still watching. So you're going to make like intervals. So, you know, like your first one is going to be, your first critical point's at -1, if you're going from kind of left to right. So in this part of my table, I want to hit everything that's before -1, so everything that's less than -1. And then I want to hit the range of -1 to my next critical point, which is 1.75. Which brings me to 1.75 as my critical point. Then I have a range of 1.75 to 3 is my next critical point. So I got x equals 3. And then I want just everything greater than 3. So this is kind of what I meant by how you set up your table. So like these sections here are your critical numbers. That makes sense. So I'll just start with them. Like, I know at my critical values that, okay, wait, before I do that, I want to set this up into like, you want to have like a test value, like a number that you're going to pick to test out what's going on in that interval. Then you want to look at what's happening with the first derivative, what's happening with the second derivative, what's happening with the actual function. So that's kind of like your areas. This is a super messy chart. Okay, so right at my critical points, I know my first derivative is 0. I know my first derivative is 0 for everything. I know for -1 that my second derivative, so if you just scroll back here, so at -1 I know my second derivative is positive. So I just did a positive sign, I don't care what the value is. I know my second derivative is negative for 1.75, and I know my second derivative is positive for 3. So just kind of want to know if they're positive or negative. Test value means what value are you testing, so we're obviously just testing the actual value in these cases because it's given. So what's going on at these points? Well, here at 1, I know I have a local minimum, kind of like that. And here I know I have a local maximum. Here I have a local minimum. Okay, and then I just test things. Like over here I could test like what's happening at -4. I know my first, and then I just plug stuff in. So I know this is going to be negative, this is going to be positive. I know my function, since my first derivative is negative, I know my function will be decreasing. And since my second derivative is positive, I know it will be concave up. It's going to look like this, kind of. So you just do that throughout the whole thing. Oh my god, it's hard to make a short video of this. It's impossible. So if I test out x equals 0 here, I know my first derivative is going to be positive, so I know my function is going to be increasing. I'll just add that. Increasing function, because my slope is positive. Then this second derivative part's tricky because you know how we have that, we have this 0.07 point of inflection. I can't write that whole word out there. Let's just say point of inflection. So I know that my second derivative is going from like positive to negative in this interval. So that's kind of confusing. So that's why you might want to even split it up farther, but you'll have like the biggest chart. You'll need to work on chart paper. So I know my graph is going from like concave up to concave down. So I'm going to have a point of inflection there. And then over here, same thing. Like if I test a value in this range, like say I picked 2, I know my first derivative will be negative just by subbing in 2 to your first derivative. So therefore I have a decreasing function. It's going to have a negative slope. And again, I have a point of inflection in here. 2.43 is my point of inflection. So on either side of my point of inflection, I know my second derivative is going from negative to positive. So that means it's going from concave down to concave up, which makes sense because my function is decreasing, so negative slope. Okay, I'm almost done. So then let's test x equals 5 here. If we sub that into our first derivative, it's going to give us a positive answer. Our second derivative positive, therefore our function's increasing because our first derivative is positive. And because our second derivative positive, we know it's concave up. It's ending like that. So just from looking at the sketches, I know I'm going like, I know my function's gonna do that kind of a shape. All right, just according to my graph here. So then what you would do to create a super duper accurate graph is you'd get some graph paper. Do you have it? You wouldn't pick values that are like negative 18 or whatever. Then you just go on and plot stuff. So you just plot all your really important points. So for example, I know I have a y-intercept at negative 18, and I have x-intercepts at negative 2, 1, and 3. Okay, so negative 2, 1, and 3 are my x-intercepts. Let's just ballpark negative 18 as being down here somewhere for my y-intercept. My critical points I know are negative 1 and negative 32, 3 and 0, and 1.75 and 4.4. So I think I would graph those next. Okay, so I got 3 and 0 is already on there. And I know that's going to be a minimum. So I know, actually, I already know that from here my graph's just going to go up. At negative 1 and negative 32, I have a minimum also. So negative 1 and negative 32, I don't know where negative 32 is, but let's just say it's down there somewhere. So I'm going to have a point right here. That's going to be a minimum point. And then I'm going to have a max at 1.75, 4.4. So I don't know, let's just say if that's 4. So like here, it's going to be a max. And that's really all we need. Like you can also plot your points of inflection too. But okay, it's going to be a rough one. I should have spaced out max values a little bit more. It's coming down. I got to go through my, oof, it's rough. Okay, I got to hit that point, and then I got to pick up my y-intercept. Got it. I got to go through my x-axis. Then that's my max. Back down. Boom. And this guy we know is just gonna probably not go like that much over, but you know, something like that. check it out. There's my graph. So I know here I have a local minimum, I have a local max here, I have a local min down here. Actually, this does not look like a local min. That looks like an absolute min. Okay, absolute min. Cool. And then I know, yeah, like my point of inflection here and like various other places. Okay, that's a pretty accurate sketch. I'm gonna end the video because it's like the longest video of all time. The end.